Oh yeah, so maybe I will just use this time to introduce you to the audience. So well, first of all, I would like to thank you for accepting this invitation and coming today for this webinar.
Thank you.
And for everybody, Professor Jacqueline Krim is Jacqueline Krim is a distinguished university professor emerita of physics at North Carolina State University, NCSU. So she holds a bachelor's degree in physics from the University of Montana and a PhD in condensed matter physics from the University of Washington. She joined the physics faculty at Northeastern University in 1985 after a year-long appointment as a NATO postdoctoral fellow at the University of Dax-Marseille too. I hope that I pronounced this well. My French is not very good. So that is in France. And she joined the NCSU in 1998. Her research interests include nanotribology, liquid film, wetting phenomena, thin film growth, and roughening. Krim has served and or is currently serving on the editorial boards for Tribology Transactions, Surface Science, Tribology Letters, Physical Review Applied, and Frontiers in Mechanical Engineering Tribology. So she has published and lectured widely on the topic of nanotribology and is the author of numerous invited review articles on this topic. She's a fellow of American Association for the Advancement of Science, American Physics Society, American Vacuum Society, and STLE, which stands for Society for Tribology and Lubrication Engineering. So with this, I would like to welcome you again, and I think now I will share the presentation on your behalf. I received the presentation, so I'll just download it quickly. Yes, so just a moment. Have you visited STLE, Professor Krim?
Have I visited STLE, the website?
Yes. No, I mean the conference this year.
Oh, the conference. No, I did not go to the conference this year.
Okay. All right, so I will share the screen. I hope you can see my screen now.
Yes.
Yes.
Okay, so I'll
great.
just make a little, how about like this when it's time to change the slide? Oh, wait, you have to change it, don't you?
Yes. So you can say a secret word or...
I'll just go like this when it's time. All right, so I'm speaking today about tribotronic control, external control of the positioning of nanoparticles within a lubricant or a fluid. So go ahead and next slide.
Mm-hmm.
I'll start out mentioning that as we certainly all know, our atmosphere is filling with carbon dioxide, and we see these reports from the International Panel on Climate Change, the number of year, the parts per million in the atmosphere. And lubrication and carbon emissions are very directly linked. Let's go to the next slide. This is another way that it's presented oftentimes in the climate panel analysis. It shows how many extra gigatons of carbon or carbon dioxide that is placed in the atmosphere, and for that, how much warming has occurred or is predicted to occur. So for example, last September, 418 parts per million, and there was a 55% chance in September that the global, not the running average, but that year's average is 1.5 above industrial times. It actually almost reached it. I think it was 1.48. Anyway, it didn't quite make it. Yesterday's value was 426 parts per million. And we see 430 on this plot is just under 1.5 approximately. Go to the next slide. So that cone there, the colored area, is 2/3 probability. And so, of course, we don't know exactly how it will turn out, but it's been doing pretty well. It has a 1/3 chance of being more than that or less. But I did, if we just draw a line through it, the temperature rise per unit carbon put in the atmosphere, rule of thumb, we get about 1,000 gigatons of carbon emitted, corresponds to an increase of about 65 parts per million and an increase in temperature of 0.75 C. That would be just a line through the middle. And I say that just kind of as a rule of thumb. We read in our tribology literature about emissions avoided, or how much the emissions are of, say, fleet vehicles. If we want to link that to, okay, how much would that increase the carbon dioxide in the atmosphere, or correspond to extra additional warming, that would be the rule of thumb. So I put a little box there. 200 passengers get on a flight for 3 hours, airline flight. 100 tons, that's okay. Okay, 100 tons emissions. So we can do it up. And that particular flight, I think we had 10 to the minus 11. But there are 10 to the 10 people on Earth, about, rule of thumb. Okay, so they might say we don't know what's going to happen, but we really don't know what's going to happen because human behavior, I name this the human behavior probability cone, is far wider than the scientific predictions. So we're capable of any of these paths. We have the technology. And it's governments and behaviors and wars and self-reliability. So that's where we are. But nonetheless, we're capable of it and we keep planning. So let's look at the next slide now. The plans, we're always planning. And here's a plan, what was it, in 2014? Of course, we had to start in 2014. If we wanted to have global warming limited to 2 Celsius, everyone has to put their full effort into it. All of the plans include the largest fraction from efficiency, 40% in this particular plan. They all include renewables. So when we think of limiting emissions, I don't know, oftentimes we think of, we just need to go solar, we need to do this. It's all there. Efficiency is always the largest contributor. And friction is about 1/3 of that. So friction is a huge component of all plans. So of course we have to enact these plans, but it is a huge component. Okay, let's go to the next slide. Friction is also keeping up, interestingly enough, from an economic viewpoint. This is a comparison of the 1966 JOST report with the 2016 reports by Ollie Erdemer and Holmberg. And because the cost of energy is going up, the economic impact of friction has skyrocketed. The total savings on tribology has remained rather constant, 1.4%, but the proportions have changed radically. And because of the cost of energy, friction is now the most expensive part. Okay, next slide. Energy is another odd thing in efficiency that has stayed. I don't know why this is, but I'll just look it up and it is. These are these energy flow diagrams put out by Lawrence Livermore. So on the left are the different primary sources of energy: solar, nuclear, hydro. This is for the United States. You can look them up for any country. And the United States consumes about 97.3 quads. That was in 2021. of which 31 quads did useful work. So if we define efficiency as the amount of useful work we get from the energy consumed, this number has stayed quite constant for decades. May have even gotten a little worse. Now, of course, on the left column, we could have all carbon-free sources and have no emissions, potentially, but we look at the efficiency as the demand for more energy goes up, and efficiency would remain paramount even if carbon emissions are solved. All right, next slide. So, can nanoparticles help? This is in the area of lubrication. How can they increase efficiency, lower friction, and what role do they have? So we're looking here at a Strybeck curve that transitions two contacting surfaces in solid contact where the friction is governed by F equal mu n. It's proportional to load. And then as the velocity times the viscosity divided by the load increases, liquid is pulled into the contacts, and the thickness there is showing. And the friction must transition over to a hydrodynamic form, proportional to the velocity. So the contact pulls the liquid in, and it transitions from a solid-solid to kind of a mixed effect where the liquid is supporting part of the load to finally hydrodynamic where it's supporting all of the load. And the nanoparticles impact every regime if they're there at the contact. Okay, next slide. Nanoparticles are everywhere. So it's not somehow in our research, we're adding them into lubricants or we're thinking of them as a lubricant additive, but they're already there. They're in wear particles. They're in earthquake faults. The micron-sized particles are in a water slurry, are the giving rise to changes in friction, stick slip, and accountable for earthquakes. The polishing agents, so it's not like they're going to be ever removed. It's more a matter of what are they doing to the friction. Next slide. They have, in some cases, just had a dramatic effect on friction. Here's a coefficient of friction. Now we know pure oil is not a good lubricant, but nonetheless, adding nanodiamonds to oil is reported in these conditions to drop the friction coefficient dramatically. This same group put the nanoparticles in their test vehicles. And you can buy them now and put it in your car if you want. They say a 3 to 5% increase in fuel efficiency. All right, well, that's the company selling it. So let's move on. Let's go to the next slide. Some of the good things that can be repositioned. They have to repel each other in the liquid, otherwise they would be coagulating and falling out of the suspension. Because they repel each other, they also provide a certain lift force, so to counteract the normal forces. So in some sense, by their very nature, they help reduce friction, increase the separation. Next slide, they can be repositioned if they're charged. They've also been used to enhance energy storage and flow batteries. So they're put in liquids and they flow around. So we can consider not just lubrication of mechanical parts, but actually flow of energy storage containing liquids from one part to another, where in one location we might want these fluids to have low friction, but when transporting them to another place, we might want an enormous amount of slip with the wall. So nanoparticles are used in many settings. Okay, next slide. All kinds of wonderful things. This is kind of like the drones instead of fireworks, right? You can show your drones in different patterns by controlling them remotely. Well, all of this is possible. Certainly the design is quite possible. I shouldn't laugh. Okay. It's not as easy as it might look, but obviously if you can make fireworks with drones, the idea of remote controlling charged particles, if there's an asymmetry in the charge, different formations can be used by remote configuration of the electric fields. And therefore, this concept of tribotronics, controlling friction, controlling the nanoparticles remotely, is quite viable. Let's go to the next slide. But intentional or not, nanoparticles are charged in suspension most of the time. And it's very commonplace for external fields to be present because of the components, because of the materials involved may develop charge, because it's an electric vehicle. We have many non-controlled or intrinsic charges and fields floating around in our systems. So whether or not one is seeking to do full-on tribotronics, just knowing what the fields are doing to these particle additives is very useful. Next slide. Here's an example of it's good to know what will happen. This is a macroscopic tribometer that our group, what's that? Got it? Okay. This is just a ball on disc, MTM mini traction machine. And we're comparing pure water to nanodiamond additives that have a surface treatment that renders them positive so that they stay in suspension, and a different surface treatment that renders them negative to keep them in suspension, right? They need to repel each other, and otherwise they'll coagulate and fall out and you're back to water. So as we can see, we looked at alumina contacts and we looked at stainless steel contacts and positive nanodiamond treatments rendered no change for alumina contacts. They were disastrous for the stainless steel, causing a great increase in friction, and negative was beneficial in both cases. So we really need to know what's going on here. All right, next slide. So challenges. This is a challenge to lubrication in general, nanoparticles in particular. Lubricants can only be optimized so far. They have to work well enough because the environment in which they're working will evolve in time. Now, it might be short times, or it might just be a long-term drift of your system. But in any case, it's not like we optimize for one particular condition because the condition will change in time. So the idea of having something that we can adjust externally rather than going in and replacing a lubricant or replacing the additive is truly ideal. It just will save all kinds of trouble and expense. That requires testing a large number of lubricants, the controls for tribotronics, accurate measurements of fields just in the lab studies. And it has to be done in a known lab environment before we can start putting this out in the field. Okay, next slide. This is the setup. I'll be showing you some of the results from today, where we performed a tribotronic study of nanofluids sliding on different metal surfaces of a quartz microbalance, put in a reference electrode so that we could also study the electrochemical properties on the surface of the quartz microbalance. And then we changed the voltage between these two parallel plates. So we have a very well-defined field on that surface. We have a quartz crystal microbalance measuring the interfacial friction at one of the contacts. It's nice because we don't just have the collective impact of two contacts touching. We actually know what's going on one contact or the other. And the electrochemical reference is telling us about energy storage and hysteresis. So these graphs on the right are the bias voltage being ramped up and down. And if there's a hysteresis, that's telling us the work done, say, putting particles on the surface or removing them. It gives us a synergistic, complementary approach to when we think we have an interpretation of the QCM measurements. They need to be corroborated by something. Okay, next slide. The measurements I was showing with the QCM, they're largely nanoscale, microscopic, and we also do a lot of just regular macroscopic ball-on disc measurements when we can of identical or very similar materials. So we can purchase stainless steel, we can purchase alumina for these MTM machines, not so much platinum. But it allows us to measure nanoscale and microscale and macroscale measurements to the extent possible. Okay, next slide. So before showing some of the measurements that we've taken this way, I'm trying to put a backdrop on this whole field. The thousands and thousands of papers are being published. And there are review articles on the properties of nanoparticle additives and long lists of, we measured this additive and we observed this behavior. And sometimes a review article seems to be a long list of 1,000 different things. There's just so many things that can happen. Alex Smirnoff, who's a collaborator on the experiments I'm showing you, he and I just submitted this mini review where we picked out 25 examples, grouped them into 5 general trends that we could see as a backdrop to our own measurements, but just what are some of the general trends emerging. Now, some of these are solid, some of these are emerging and may be correct, but let me just point out what they are. Okay, I'm quickly going to go through them, the papers there. First one is that the theory of a quartz microbalance shaking back and forth, that's a nanoscale approach, has developed, particularly the group of Johannsson, to the point where you can take a nanoscale spherical object, like the size of a nanoparticle, and put it up and down on it, and measure the damping forces and compare nanoscale friction to macroscale. What's nice about a QCM is you can also do the old school Da Vinci and just put a slider on it and measure friction F equal mu n. So that's pretty recent developments that we have these, we call it for the, in the different regimes, the boundary layer where there's direct solid contact. Next slide. Next, okay. There are also measurements and increasing knowledge of how much slip is occurring at a solid-liquid interface when nanoparticles are added. And this slippage at the interface or above the interface, and again, it's a variety of theories, is starting to have a key role in what the friction lubrication properties are at that interface. Next slide. As slippage is increasing in importance, rolling, which has been talked about for decades, either doesn't do anything or it might actually increase friction. It's kind of time to put this away and quit. Well, all right, quit it. Let's not even focus on it now, but it's kind of just gone out of anybody looking for it showing to help friction has not found it. Put it there. Next slide. One thing that's emerging in a large trend is when the charge of the nanoparticle is changed. Words are astonishing impact on friction, dramatic, small changes in charge surface groups, charge of the counterface materials are just having massive effects on the friction levels. So that is turning out to be one of the big ones. Next one. That does mean you can tune friction, but it also might mean you don't want to tune friction. There are some publications, not the one I'm showing, where these are carbon nanoparticles with different surface treatments. But there are some articles that show that if you destroy the crystalline structure of the surface coating, you can develop a resistance to electric fields. So you might not want your particles to be sensitive to tribotronic effects. But in any case, here we see the particles on the bottom form a film and lower the friction, and then up above, I think they say they're even abrasive. So again, this is considered to be the huge opportunity because there are so many surface treatments, particularly with carbon particles, so many ways it can be custom designed with dramatic differences. All right, next slide. Let's go back to our setup now, and I'll show you some of our measurements we've taken. And for really fundamental studies, in this case, we're studying a lot of ceramics on platinum. And again, there are two crystal QCMs facing each other. And we're applying a voltage and measuring the slippage at the interface. So next slide, please. QCM, it's about this 1 centimeter across. And on the top left, we see it vibrates horizontally in the fluid with the nanoparticles. And it really is very similar in speed, loading forces, etc., to a contact that I show below of two surfaces in the hydrodynamic regime. It's taking measurements of what is the slippage along one of those interfaces. Next slide. So when those particles and when that interface starts slipping, rather than staying stuck at the interface, the QCM is quite sensitive to that. We measure the frequency and the damping forces. So if this were superfluid helium, there's no response at all. It's just perfectly slipping. Otherwise, if it's a no-slip boundary condition, we have a very well-documented exponential decay of the motion of the liquid into the bulk. Next slide. The setup can be quite basic. Here is a very basic setup measuring the frequency and amplitude, which shows up as a voltage of this oscillator, a drive circuit. Dip that quartz microbalance into a fluid. It can be oil, it can be water, base stock fluid, and then add nanoparticles in. See what happens. Next slide. What happens is the resonant frequency will change, and it was already dragging along some of the bulk liquid. So it might pick up some extra drag from particles, or if it's a very slippery interface, which we've only seen on occasion, it might decouple the whole thing from it and look like it loses mass. Meanwhile, the dissipation or the drag forces on the quartz microbalance, if you think of your hand swimming, the drag forces through water, they ought to increase if you're doing it through mustard or something. But sometimes when we add these particles, we see the drag forces go down. Next slide. So here's an example of these drag forces going down. As a function of time, we've dipped, say, in this case, platinum QCM into water, and that was the left-hand blue area. We add 0.67% titanium oxide particles. Those were 40 nanometer. We see a drop in the frequency, but not as much as would be expected for the increased density of that liquid. And more remarkably, we see a drop in the resistance to motion, even though it's a more viscous material. So you would think that the drag forces would increase if you're putting your hand like through thicker material, but in this case, they actually decrease due to the presence of the titanium. On the bottom, D of F of R over F of R, we're using that as a gauge of how much the quality factor changed, divided by the quality factor, and it went up. It's a better oscillator with those particles present, and we're using that as a gauge of lubricity. Okay, let's go to the next slide. We tried this out with the macroscale tribometer for some uncharged particles. These were iron oxide with steric coatings. So the gauge of how much the quality factor goes up with percent nanoparticle added was proportional to how much the friction was reduced in a macroscale system of the same materials. So on the right, we used alumina. These were alumina contacts. We wanted things to be free of charge. So these pictures are for representation only. And then on the left, we just did this simple nanoscale experiment. So what are we seeing here? We're seeing that something about the sliding at the interface also shows up on the macroscopic scale. It's not cause and effect as much as if the interface is sliding, it's impacting both scales. Next slide. So we can take a look. We carried out those experiments as a function of velocity to see which regime we were in the macroscopic scale. We thought we would be in the hydrodynamic regime because that's where it makes total sense that a QCM would match up with a macroscale measurement. But interestingly, they were in the mixed regime. So we're already seeing an effect of adding nanoparticles in a mixed regime where the liquid is providing support for the normal force. So it's already starting to lift off. One of the questions that we don't know the answer to is how extensive of this range does this linear relation go for? But again, it's not a cause and effect so much as if slipping is there, it will impact everything. Next slide. Oh, we can move on. This is a comparison of positive and negative. I show the picture of the wetting properties. They will wet differently if they lubricate differently. We'll get back to that later, but let's just go to the next slide. Okay, so we took these different wetting and different charged particles, aluminum oxide and titanium oxide, and measured them on a quartz crystal surface with different bias levels, and we should see very different properties. So let's go to the next slide. And we did. I'm not sure that's a surprise, but it's interesting to look at it. Titanium oxide, the black negatively charged, the frequency doesn't drop as much. Remember, if this were superfluid helium, it wouldn't drop at all. Alumina, it did, a positive charge. The turning on an attractive field caused them to drift in opposite directions, both the damping forces and the frequency. So we're expecting opposite behavior and we're observing opposite behavior. Notice that when we turn on that field, the x-axis there is over tens of seconds. Okay, next slide. This is just documenting. I won't do too much of a data dump here, but maybe I'll say we took lots of measurements to see what would happen for different frequency responses. Impedance spectroscopy is very revealing of the nature of the response times of the system. And if we go to the next slide, there is something that's interesting that pops up at certain frequencies. You'll see the double peak on the titanium oxide that's not present for the alumina oxide. This is the left middle panel as the frequency is changed. And that's showing up at the slower frequencies in the resistance. And that's going to be an important key point to come back to, that double peak. Let's move forward to next slide. Again, there's a feature showing up at slow scans in the titanium oxide that's not there with alumina. Based on all our measurements, combined with electrochemical, combined with all kinds of things. Let's just leave it at that. Getting electrodeposition at slow speed and certain voltages. And imagine what that does to friction when your system goes from a repellent nanoparticle system that's slippery to all of a sudden it collapses and penetrates the water layer on the surface and forms a film that locks in. Let's go to the next slide. Okay, alumina doesn't do it. Let's go to the next slide. These are here for the record to show we were very careful about this. It's a reversible deposition, completely reversible, because it's good if you're interested in energy storage. Possibly good if you're interested in friction, which I'll get back to. But it's important to know that that totally changed the interfacial properties simply by going slow enough, applying that field for 300 seconds. Okay, next slide. And again, these are here to say that we have been careful and checked this by different methods of cyclic photometry to look for electrochemical properties that should be present if it's electrodepositing. Next slide. Okay, this one. We checked this effect for different size nanoparticles of titanium. And the 5 nanometer sizes, no matter the range of conditions we looked at, they did not show this deposition. We could press them to the surface, we could see a lubrication effect, but they never deposited. Meanwhile, for the larger ones, the 100 nanometer particles, even in the literature, we see good things happening, but for our system, they did not remain in suspension. They were just there for minutes before they needed stirring to be put back in. Maybe this is the explanation. Maybe some of the test setups at the macroscopic scale are constantly stirring them anyway. So there was no problem. But for us, they were very lubricious, but they didn't stay in place. Okay, next slide. This is showing one result that we do want to comment on. You never really know if the friction will go up or down when we deposit alumina on the surface. By adding the nanoparticles, the friction went up. On some of the ionic liquids, if you get this layer deposited on the surface, the friction actually goes down. So again, it's a matter of screening required. Next slide. Nanoparticles in oil. You can watch these effects. and we see quite a bit of abrasion. That was the main observation for the liquids. And again, knowing what's happening, they were abrading and smoothing the surfaces. Next slide. So I'm going to get to some of my conclusions and go over them a little more slowly. The usefulness of this as a rapid screening material is nice. You're looking at many hundreds of measurements summarized in this slide of showing how much the quality factor increased for a particular system when nanoparticles were added to different surfaces. And different kinds of nanoparticles, different surface charge. Sometimes the quality factor went down, those are the negative numbers, sometimes it went up. And we looked at this and said, okay, let's try to predict if this is going to now predict what happens in a mini traction machine. And the other thing we noticed about this was that the range of properties of all these things we've looked at, silica, platinum, nickel, alumina, they had many properties from insulator to electrical conductor. And the properties of the nanoparticles are the most consistent. They dominate the system. Electrical properties, in particular, of the combination of the macroscale and nanoparticles, start to really dominate. Okay, next slide. That's what I just said, okay. Those two circles in the middle, the dashed circles, they represent spot checks where we went back in and tried it out on the macroscale MTM. Notice that's alumina. So that's something that the company sells for alumina contacts. And we did see the rank ordering the same. It's not like we saw an exact prediction of what the friction would be, but we did see the rank order. If it increased the quality factor in the QCM when added, it would decrease the friction on the MTM, or at least not increase it as much. Another thing we're seeing in some of the theories is a computer simulations. They'll take the background and have water and replace it with oil, and the rank ordering of the effectiveness of the nanoparticle stays the same. The absolute values are all over the place, but the rank ordering appears to be staying intact. Okay, next slide. So based on this, I'm just coming to conclusions, and I'm going to answer a few questions that I commonly am asked in the next couple of slides, and then that's it. But if we're using the nanoparticles, we have to pay strong attention to what they are, because they are having a dominant effect. As I just mentioned, the base oil appears to have a lesser effect. All of these obviously have an effect, but if one type of nanoparticle is better than another, all things being the same, you might be able to swap out fluids. Time response, I'll admit I was underwhelmed, maybe even disappointed that this is happening over tens to hundreds of seconds. I thought Tribotronics meant like a rapid response team coming in and changing, because in real time we can measure what's going on, you know, in fractions of a second. But now, oh, nanoparticles, come on in. So that's, but okay, that's just me. Lots of people have told me that's okay. There are plenty of approaches. The nanoparticle size and charge are very interrelated. They have major impact on lubricity. What's kind of interesting is when you put the surface treatment on, it changes the size of the nanoparticle and it changes the charge. So what you used to have, the treatment on one core particle and a different treatment on a different core particle, you end up with very different size and charge. So it should be no surprise that they behave differently. Okay, next slide. I'm just going to finish up with what are some of the applications here. So I'm asked, well, how would I use this if I'm trying to apply it? Hugh Spikes and his colleagues have been, they don't call it slip and grip, I call it that. They call it half-wetted. Half-wetted means that the lubricant wets one of the counterfaces and does not wet the other side. As I showed a picture of droplets, when we add the nanoparticles, it radically changes the wetting properties. Nonetheless, I call it slip and grip. Okay, slip and grip. If you know that your lubricant is going to be very slippery, that's good. It'll reduce the friction. But it's also bad because your lubricant might not even make it into the contact. It's so slippery. So Spikes has demonstrated that by having a non-slip on one counterface, it can be pulled in to the contact and then the friction is low. So that's one way, and the QCM can show that this can happen automatically by moving particles. You can deposit a film and get high friction. Okay, next slide. Okay. Another way this could work, well, I name this one illuminate and then applicate. Okay, you can change the charge on the nanoparticles in a remote location and then flow them in. Don't have to do it in situ. So it can be prepared in advance with illumination. Maybe that would be faster. All right, I think we better finish up here. So next slide. Just a summary of our results that in our lab, we've successfully repositioned nanoparticles with the external fields, and we've successfully tuned friction. Time scales are very sluggish, in my opinion, tens of seconds. And it's quite variable, but the nanoparticles are dominating the response. Some sizes, you get the electrodeposition and film formation totally changes the friction, and rapid screening has been achieved. So I'll just, next slide to thank my next one there, let's go there, next slide. One more, there we go. I do want to point out, Alex Smirnoff and I have collaborated on this, and two PhD students, Biplov Acharya and Caitlin Seed, what I presented of our own research today was their PhD research. So how can I not credit them with doing all these measurements? So, all right, thank you. Questions? All done.
Thank you very much, Professor Krim. So I forgot to mention everybody that if anybody has a question, you could write a question, but you could also raise your hand and then you can just ask your question by speaking. But I think there are some comments or questions here. Let me take a quick look. Yes, we are getting some comments. Let me go and find Ahmed. Just
wait, maybe I can see that. Oh, never mind. I won't. There's a hand raised.
Yeah. So let me see. There is a hand raised.
I'm afraid to touch any button. I might just vaporize. So I'll let you know.
Oh yeah. So I think Ahmed raised a hand, and then I think you can unmute yourself, Ahmed, and then you can ask the question. Ask the question. Ahmed, can you hear us? If not,
Okay.
then I will. Oh yeah.
Yeah,
we can hear you.
Yeah.
A quick one. This nanoparticle the technology, if I should call it, is there any preferences like among the different types of additives like anti-wear or 4-point dispersant or anti-friction, or what are the effects like size-wise or impact on the finished product? Like if you want to make an engine oil.
Yes. Okay.
So
The first, are you finished? Or is it
yeah, go ahead.
Okay. First and foremost, it has to stay in suspension. So there's enormous focus on ways, especially carbon nanoparticles are good because you can have so many different types of surface functionalizations. They're really the heartland of many studies. And then there's sort of a trend showing that the larger, the better. It has more charge. It can be less susceptible to the smaller pits. So the trends are to tune the dispersant to keep it in suspension. And that involves a lot of repulsion. But carbon-based systems are probably emerging as quite preferred. Alumina oxides are also quite popular because they are capable of manufacturing in very large quantities. But the idea is to put in the minimum to keep the costs down, and every little bit helps.
Thank you, JK.
Thank you for the answer. I think we have also a question from Sadhu. You can unmute yourself and ask a question. Yeah, Sadhu, you can ask a question if you want. Otherwise, I will read the question.
Hello.
Oh, yeah, we can hear you. Yes.
Yeah.
Professor, this is Suvin. Professor, the doubt for me is, suppose we are using MR fluid, that is magnetic rheological fluid, or if you are mixing these particles to the fluid, how to functionalize these particles so that to avoid this deposition, as you mentioned, how to approach this issue so that we can avoid the coagulation or deposition of the particles in the fluid?
I would say rapid testing. I cannot say in advance how to avoid it, but the coagulation has to do with a lack of repulsion. So these two effects, if you can think of it, the two effects are almost counter to each other. So you want strong repulsion. And that's actually good for friction too, because a strong repulsion provides repulsion in the vertical and horizontal direction, so that helps with the normal force. But this strong repulsion also has makes it more interactive with the substrate, shall we say. So you could functionalize the substrate, you could just do rapid screening and apply voltages and see what doesn't stick within a range of parameters. But at this point, we are not, how do you prevent it from, how would I prevent it? Well, one way I prevent it is to just use an uncharged surface.
Okay, yeah, thank you very much, Prof. Thank you for the input. All right. Yeah.
Thank you. And we have another question. I think I will read it from Sadhu. Nice presentation on nanoparticles effect on friction. How carbon nanotubes will affect the friction? I'm assuming that's the question. Nanotubes, carbon nanotubes. Can they be used?
I'm going to answer that question with a reference. Do you see do you still have my presentation somewhere? If we go to the references, there is a fabulous review on all the different dimensions of carbon. So let's go
Yes.
down to the next slides. Wait, I'll
Yep.
find it. Not that slide. No. Go down. No, one more. Yes, I think we're here. Whoa, back up. Nine
Yeah,
hole.
sorry.
Okay.
Yeah.
This is a really comprehensive functionalized carbon nanostructures, and we're talking in every dimension, 0, 1, 2. In fact, this group, or these authors, looked everywhere for signs of rolling that helped. And I think they even make a comment of wondering why experimentalists still think rolling helps. But in any case, they go into great depth on carbon nanotubes and different shapes other than spheres, and how you functionalize them and the impact on atoms. That's 2022. Everything that is known is in that paper, I think. So I will not attempt to answer that. But that's my answer, if that's okay.
Okay, thank you. So I think that we will upload the recording of this webinar to the website. So if anybody by chance forgets the name of the article. Yeah.
Okay, there's a hand raised here. I don't know who that is.
Yeah, just a moment. I will stop sharing and then.
Yes, please do upload the, that would be nice.
Yeah, I think Ahmed is raising a hand again.
Okay.
If you have a question, you can unmute yourself, Ahmed. Yeah.
Yeah, thank you very much. Frankly speaking, I am attending this for the first time, and I have been in lubricants business for the last 43 years, surprisingly. Firstly, I can get this recording, I understand.
Yes, it will be uploaded.
Email.
Yeah, you will get an email, yes.
And secondly, is there any membership or something where I can participate in your activities or share my thoughts?
Of course, I think there is the Society of Tribology, Lubrication Engineering. There is on TriboNet. You could also, if you have any ideas you would like to share, you could also write an article or a comment. So you can write administration at tribonet.org for that.
Oh. Okay.
I'd like to make a comment that I haven't been in lubrication for 43 years. I've been in atomic scale friction. And Alex and I have posted this preprint where we made these general observations. It's on Google Scholar under my name. You have so much experience. Nobody's made any comments. But if you see anything blasphemous there, this would be the time to say it and write a comment before this goes into print.
Sure. I'll come back on it.
Collective wisdom is so
yes, definitely.
perished. Yes.
Yeah. Thank you.
Thank you very much.
Yeah. And I think if you allow me, we are out of time, but just one question that is of interesting from my side is, what is more efficient, reduction of friction or increasing the lifetime, according to the analysis that you showed in the beginning of this presentation?
Reduction of friction.
Okay, so.
I am at meeting after meeting where scientists are reporting, engineers are reporting that our material objects are lasting longer than we want them to. And so we're getting rid of stuff because we're just bored with it, not because it wore out. So wear has been actually largely tackled, but friction was taken for granted that energy is so cheap it didn't matter. Definitely friction.
Okay, clear. So we focus on friction, right?
Yes. And eat all your food. There you go. For global climate.
Yes. Okay. Clear. Well, we are a little bit out of time, so I'd like to thank you, Professor Krim, very much for this presentation and for your work, for the contribution to our planet, to the tribology. We will upload this presentation or upload the recording of the video on the TriboNet. So if anybody would like to take a look again, or anybody's has missed the presentation, there will be a chance to take a look at it. With this, I'm finalizing then this webinar. Thanks everybody for attending, and have a nice weekend for everybody. I think there are several comments that thanks you, Professor Krim, for the presentation.
Thank you.
Yeah.
Okay.
Okay.
Awesome. Thank you.
Yes. Thank you very much.
Bye.
Bye-bye.